Hello, my name is Alan Wade, and today we're talking about the hydroplanet model. This is from the Universal Model, A New Millennial Science, which is a book that was recently published and is changing all of modern science. And for this presentation today, my name is Alan Wade, as we talk about the hydroplanet model. The hydroplanet Earth says that instead of magma in the center of the Earth, there is a solid ice core and liquid water in the outer core of the Earth. And then in the mantle, it's rock and water. So that's a representation of what we believe the Earth, the center of the Earth, is like. Much more so than magma, this inferno in the center of the Earth. So, and if the Earth's been around for 4.5 billion years, it's unlikely that magma would still be hot. So we had another presentation about that a few months ago, and you can check that out on our YouTube channel as well. But we're going to jump right into it here. This is a pretty dramatic quote. "Deep inside the Earth, the pressure is excruciating, but it contains something surprising, at least to modern scientists. What's the last thing that you would expect to find in this hellish environment? Water. Vast amounts of the stuff. In fact, more than 400 kilometers inside the Earth may be enough water to replace the surface ocean more than 10 times. How much there is down there is still fiercely debated, but these inner oceans could help explain long-standing puzzles about Earth's formation. Many different strands of evidence point to the existence of this hidden water." So that's a pretty dramatic quote from the New Scientist, and it's completely contradictory to what is modernly taught to our third graders as this magma, hot, molten center. And even in their quote, they're describing it as high pressure, hellish environment, hot inferno type environment. But they're saying that it's surprising because it's so different from what they're saying there. Here's another good quote. "It was no ordinary earthquake that struck near the town of Chichi in central Taiwan on the 21st of September 1999. The ground seemed to explode as huge boulders were flung into the air, and flashes of light lit the night sky. Taiwanese geologists have now explained this unusual and terrifying geological event. The boulders were powered by high-pressure steam. They say as sliding rocks heated groundwater to a boiling point, when the dust settled, deep holes pitted the ground, as though columns of rock had been blasted out. The friction generated by the rock faces slipping over each other in the quake made the ground so hot that water turned almost instantly into steam. And steam, when it expands, or when water changes to steam, it expands 1,700 times the volume. So a very tiny bit of water will expand 1,700 times the volume. So you can understand these huge boulders being exploded out of the ground because they're being forced by the pressure of that steam. And so one of the factors that's important in this hydroplanet Earth is that we have hydrofountains that explode out of the ground. And we actually can see fossilized evidence of some of these hydrofountains. You can see the little man there at the bottom looking up at this tall column of white sandstone. There's some brown sandstone around the base of it there. So this is a fossilized hydrofountain. It's located in the Kodacomb Basin in southern Utah. And it's a vertically oriented pipe of hardened rock that was formed in a hypertherm, because we know how rocks are made, how quartz crystals form, and it's under 5.5 miles of water. So this was probably like those holes or pipes, tubes in the ground, where something, a big boulder exploded out with a lot of steam, and then eventually sand settled back in, and it was crystallized during flood conditions with 5.5 miles of water over it. And so, and then the dirt around it got washed away. So, we're going to be exploring the hydroplanet model today and looking at a lot of important factors. Now, this is one in the Long Valley, California. They did a borehole, and they were trying to get down to magma. You can see in the little diagram, it has congealed magma, is that kind of reddish pink, and underneath that is partially molten magma, and that used to be red. They changed, they made it white again, because as they drilled this borehole through the basement rock, they thought they would get down to the magma and be able to generate a lot of thermal power, or use thermal generators to generate electrical power from the heat of the magma. In fact, that's why they picked Long Valley, California, because they thought it was over one of these magma plumes, or where there was it was close to the surface. And so it's interesting that what they actually found, instead of partially molten magma, is they ended up finding evidence of water flow down in these depths. It was about about 10 miles deep. Now, another evidence that we have that the Earth is filled with a liquid is that there's an equatorial bulge, because the Earth is not a perfect sphere. Imagine on the right shows the 27-mile or 43-kilometer equatorial bulge of the Earth. And so that's evidence that it's a liquid inside the Earth. And this is another borehole. The Kola well and our own have shown that the deep crust of dense hot rock is definitely not the case. There are large amounts of saline brine in the crust that migrate, carrying metals around and depositing them as minerals. And so this brine is salt water, basically. So we're finding lots of that deep in the deep as they drill these two holes, one in Russia and one in Germany, and that's what that's talking about. And then, of course, Long Valley, California was another one. So the textbooks could be wrong about what's in the center of the Earth. And here's the distribution of water in the Earth. This is what modern geology says. It says that 95% of the water, is almost 96, is contained in the oceans that are on the surface of the Earth. Then there's 2.9% in glacier polar ice, and underground water 1.05%. And then we also have some water in lakes and in the atmosphere, in our clouds, which we're experiencing today here because it's raining outside. But in the universal model, and based on the research and like that first quote that we went through that said it could replace the surface oceans more than 10 times, it changes. So the hydroplanet model says that the underground water is 99% of the water in the earth. So that underground water moves up to the top of the list and makes up 99% of the water on the earth, so that the water in the oceans is only about 1% of the water. And so glaciers and lakes and atmosphere is even much less, way under 1%. Okay, the textbook view that the Earth spent the first 500 million years drenched in magma could be wrong. And again, these are quotes, this one from Scientific America. And one of the real things that kind of shows that there's not magma inside the center of the Earth is they can do tomography of the Earth. This one is tomography from Central America, and up in the upper left, where you see it says trench, that's where there's like an earthquake fault line. And so you can see it's hot right there where there's a significant amount of fault line and what we call frictional heating. And then down below here, the cooler areas is where there's a lot more water cooling it down. So, and this is going down, this is going through the mantle here down to the core. So that's a cross-sectional view right across Central America. So it's one of the evidences that we point to show that although there are sections where it's hot underneath the surface of the Earth, those tend to be close to the earthquake fault lines, which we say are getting heated through frictional heating, the pressure of these continental plates pushing against each other, because that's where that trench and the earthquakes are. Those little white dots in there are the earthquakes. Okay. So deep earthquakes is another important factor. The earthquake centers at depths of 435 miles or 700 kilometers don't make sense when magma is supposed to be present there. And the reason, shown by the honey, is it's difficult to fracture honey. So if you had molten rock, we wouldn't be hearing and picking up on our seismic measuring devices that they're having these deep earthquakes. So there must be something other than magma down there. So Earth hydroplumbing system is confirmed. In Greece, Brodsky has found that the hot springs are fueled not by magma chambers, but by the changes in the pressure of fluids coursing through underlying crystalline rocks. So the cracks and fissures that go underneath the ground are mostly, a lot of them are filled with water. And that plumbing system, or hydroplumbing system, says that those are connected. And so as you have the pressure building up in one area, then it spreads out and affects other areas. So in the hydroplanet Earth, we have seismic waves right here are measured because they go through ground easily. But when they hit water, then we can't really measure them. Okay? Because it's the wave stops, those seismic waves. And so when there's a fault line, we can kind of sense that because there's water that we pick up. And so as we go down deeper, we get more resistance to our seismic waves because we're getting more water content in this lower part of the crust. Okay? And then even down into the mantle, there would be a lot. So this cross-section comes from scientific research studies, And you can see over here, it's just a very small fraction of the Earth's crust because it's barely showing the mantle. So this is only 30 kilometers deep where we start to go into the mantle. Any questions? Okay. Yes?
So you're talking about how the fractional thing with the honey.
Right.
I don't see if the center of the Earth is water. How does having magma versus water?
So the
how can you have a earthquake 435 miles deep when it's water?
Yeah, very good question. The 435 miles though would still be in the mantle part right here. See, so the crust here is only going down 30 kilometers, and then the mantle you can see is much deeper than that. So there can be rocks, because there's probably rocks and water and ice sections, and those the ice can break and crack, and the rocks can break and crack or slip, and so you can have those earthquakes down much deeper even than this is showing.
So
let's see,
having it like going more and more liquid as you go down. It's solid, and then it gets more liquid at the end.
Yes, yeah, and that's why in this picture, this one is going much deeper. We don't have the measurements, but the 30 kilometers ended just in the surface here, and this is going through that mantle, and so the water, where it's just water, would start here in the core. Okay. Yeah. Okay. So this is that area where they're finding earthquakes down there, 425 miles deep. It'd be in this section. So, and it is pretty phenomenal to think about how far that is to the center of the Earth. Somebody related it to going from Florida. I think they said St. Petersburg, Florida, to Anchorage, Alaska, would be like halfway through the Earth, to get to the center of the Earth. And so it's a long distance. Okay, so let me go back here. Okay, that's where we were. All right, and this again, just a small portion near the crust, but this is the Miyake-jima volcano hydrothermal system. And in this, the diagram is a cross-section of the top of that volcano near Japan prior to its eruption, January 8th of 2000. And they found that the fluids were moving down here and then up in this area. And so there was this hydrothermal system that was heating the water and making it circulate like that. Okay, so like from the cold waters of the ocean out here, and then getting closer to that island and coming up through. This next picture is going to show the eruption of that same volcano, and you can see that Miyake-jima, I'm not sure if I'm saying that right, but tiny island here, kind of south of Tokyo, and so to the southeast of Japan. And this is a closer 3D diagram of that inset. There is a 3D of that little mountain, and when it erupted, you can see the steam that's being put out there. They can find it on the NASA satellites. That steam explosion was so huge, it's stretching for probably hundreds of miles there. Okay, so these steam explosions, steam is a big part of what we usually call volcanic eruptions and the volcanic ash that is coming out of volcanoes. Even when we have lava coming out, like 90% of it or more is steam. And that's because that steam, that water turning to gas, explodes and expands 1,700 times the volume. So it forms this hydrocrater, a circular surface depression formed by the phreatic explosion of underground water through a diatreme. And the diatreme is the funnel shape that you see here. So we've got plates moving along these fault lines where that lava is being created through frictional heating. And then once that reaches an area where there's some water, it turns it to steam, and that explodes out, forming the huge cloud and breaking the rock in this funnel-shaped form. So we call that a diatreme, and then the crater that it makes is a hydrocrater. So those are important features that you need to remember in the universal model, because you'll come across them frequently. Okay, so 3 requirements of a hydrocrater formation. One is that you need water, because that's going to turn to steam. You need a fault line, because that gives you frictional heating. And then it forms a diatreme, which is that funnel-shaped tube. And as we look at craters around the world, you can kind of see where on this that the pock marks are hydrocraters that follow a fault line. So there's a whole line, a whole string of little craters formed here. And we see things like this all over the moon and stuff. And so why are these in lines and rows? And that's because they're on a fault line. And so it's exploding and forming a little hydrocrater. And it may do it one time here, where that's the hottest spot, the closest to the earthquake activity. And then maybe another time way up there. And so over time, you get a whole bunch of these in a line. Okay? These are some off the coast of California. Okay? You can see, you could draw lines through a lot of those. Okay. Shoemaker, famous for studying Arizona meteor crater, said without impact, Earth, Mars, Venus, and Mercury wouldn't exist. So he can't even picture all of these planets in the solar system without having a lot of meteorite impact. But as we go on in this presentation, we'll look at some of those planets and their moons even, and see that water is very important. So the impact pseudo-theory says that impact theory is unsubstantiated because there's a lack of observational data. No one has ever actually seen a large hypervelocity, so that's super high speed, because if it's a rock coming in from outer space, even our astronauts, right? When they're on the space shuttle, when they're coming back into the atmosphere, the gravity starts pulling them through that atmosphere very fast, and that's why they need all the heat shields and stuff, because they're going so fast that they heat up. Just the air passing by them makes it extremely hot. But nobody has ever seen these high-velocity impacts and performed a close-up observation on the impact crater. So we don't have a lot of data. We see a lot of craters on the Earth, and most people assume that they were made by a meteorite impact. But I think the one in Russia recently, or a few years back, is the only one that we actually, tracked coming in and know of on the Earth. And so we're trying to test these. We're looking at them. So the comet Tempel 1 was struck by a deep impact space probe, and it was designed for this high-speed impact study Although the project revealed some of the comet's secrets, no photo of the impact crater were obtained, and thus the mission provided no evidence of what high-speed impact craters would actually look like after that impact, right? Because the rocket that we sent there crashed into it and then was destroyed, and so we didn't get the pictures. But this is on Jupiter in 1994. We did track this impact, and you can see in the center here the Shoemaker-Levy before impact, all these lights from this comet as it's coming in. And up at the top, we have the before at the bottom, no surface differentiation, but then the dot that's created after the impact and how it spreads as it goes later going up. Okay, so impact and the dust spreading up and around and into the atmosphere. This is with the infrared readings. More than one location is where that hit. So that's why we have different spots tracked along on the picture of Jupiter there at the bottom. Now, an interesting thing about impact craters, when we look at them, they have a very specific signature. And so we have pictures here of Mars at this site before it was struck. You can kind of reference this little crater up here in the upper left of those pictures. And in the center here, this is before, and then after that tiny dot in the center is where the meteorite actually hit. But an interesting thing is that there's a V right here at the top, this V impact. You can see there's no debris that was deposited in that V. Because as the meteorite came in from this direction, it hit here and it did spray some back, but it didn't spray it in that V area back there. And you can see most of the ejectite was sprayed forward from the direction of the meteorite coming in. And so, and in different directions based on, how the rocks broke and, the shape of the meteorite before it hit and the density of the rock that it's hitting into. So spraying some, but away from that V impact. Okay? I think it's pretty interesting. Now, we have done some hypervelocity studies, like with guns, and then this picture is actually from NASA satellites, microscopic view of high-speed impact craters that appeared on a NASA satellite, and it shows clear evidence of melted glass, basically. When it melts the surface there, it turns to a glass. So both observational model circulation indicates that the relative volume of impact melt increases with the crater size. Quartz forms a definite melt region around the crater in the middle of a larger spallation zone. And then the last quote, copious amounts of projectile melts are preserved as thin glass liners draping the entire crater cavity. Okay? So do we see that melted glass in meteor crater? And the answer is no. We took a tour up there and we didn't see any glass. But there should be, if it was indeed a meteorite impact at this hypervelocity. Astronomers seem to invoke collisions, however improbable, they cannot explain odd features of the solar system. So the definitive impact criteria is shatter cones, PDFs, which are planar deformation features, and these are things that are seen microscopically, and then coesite, which is a type of rock as well. because these geological items are also found in other natural environments, such as hydrocraters, then it's not so definitive, because we can find them. And so that's the big flaw in the impact criteria. Several geological features, including sedimentary cone-in-cone structures and percussion marks, again, percussion, right? We think of drums and stuff, so that's impact. Okay? Those percussion marks may resemble impact-generated shatter cones, especially inexperienced workers may mistake such features for impact deformation. So you really need somebody who's experienced looking at these, because it's hard to tell and hard to differentiate, because it could be formed different ways. But as some examples here are the crater doublet evidence. And this is where two craters are found together. Now, first of all, it's kind of unlikely that you're going to have two meteorites hit real close to each other. But this is the bottom left here is actually showing an experiment where I think they were shooting bullets, and it formed a little wall in between, because when the hypervelocity hit here and here, then it ejected the dirt out of that crater, and it kind of hit it together in the center and then dropped down and formed that little wall in between the two craters. So that's what happened when two hypervelocity impacts happened together at the same time. Yeah, so like two bullets, yeah, being hit at the same time, yeah. All right, yeah. Thank you for making that clarification. Two bullets at the same time. And so where are walls like that found on the moon? If you have, like maybe it's a meteorite that comes in and breaks apart, and so that it lands as two meteorites at the same time. But a lot of the craters that we find on the moon are formed in different ways, and one of the things that we'll see is these craters. You have a large crater, and then on the side, right on the edge of it, you'll see this little crater. Okay, and we actually see that there, down here and down here in the bottom picture that's there. Each of those are a large crater with a smaller crater on the side. And if it's a hydrofountain crater, diatreme, right, it blows out this big, huge diatreme shape. And so the rock has been broken, but it settles back down into the crater, and so it kind of fills up a lot of that funnel shape. And so you have this kind of smooth bowl-shaped bottom, but the shape that the rock is broken in is this huge V. Well, if you have some more earthquake activity and the water being turned to steam, it's going to explode, and it's going to follow the path of least resistance, which is actually going to be right along the edge of that V-shaped funnel. It's going to shoot right up, right? It's not going to push all of the rocks out of the way here in the center. It's going to travel right up the edge there and explode out the side, and that's why we're getting these craters, the big crater with a little crater on the edge. Okay? So it makes much more sense to see that as a hydrofountain crater, because it's unlikely that a smaller meteorite would hit right on the edge of a big meteorite impact crater, right? Okay? And even up in the upper left here, we have smaller craters always intrude into larger craters. So some of these are near the edge, but not really right on the edge. That one kind of is. Here's a pretty large one on the edge of this one. So that's pretty significant. Now, shatter cones was one of the things they said was definitive evidence, but the shatter cones are, and that's kind of that idea that if you melt something, like you see it in a water droplet, if you drop water into a pond, it'll hard that it kind of bounces back up in the center, and the drop will come back up. If you've ever seen a picture like that. And so that's where the idea of these shatter cones or central peaks are. And we do find a lot of craters with central peaks, but a lot of times the central peak is not so central. Like on the left there, we have Crater Lake in Oregon at the bottom, and you can see this little central cone that sticks up out of the lake is way over to the side. Okay, so it doesn't make sense if for a meteorite impact to form that central cone. So it's formed way over on the side, which actually does make more sense if it's a hydrofountain impact. And it also makes more sense that we have water in the lake of that crater, right? So we had a great big explosion, and then maybe some other little explosions that formed that little mountain in the center. Okay, so we're seeing this on the lunar surface. These other two are from the moon and lunar surface. So we've got a larger crater, and the cone is set off to the side a little bit. Okay. So here, complex crater evidence. There are many areas of uncertainty in how such features as central peaks, pits, and rings originate, because sometimes it'll be in like a target pattern where you have a crater within a crater within a crater, okay? And again, if you have multiple explosions from a hydrofountain, then that makes sense and could form easily. But it's a little harder to explain that if you're thinking that it's a meteorite impact, because how would it hit that exact same spot? Only smaller, right? We have to get the largest crater hit first, and then a smaller crater, and a smaller meteorite, and then a little smaller meteorite, and then the smallest meteorite hit last, right in the dead center of where all of those others hit. Little unlikely, don't you think? Yeah. Okay, Enceladus is one of the moons of Saturn, I believe. And it has hydrofountains on it. This, the inset here is a picture showing actually how big that hydrofountain is. It's almost as big as the moon itself, right? So here's the moon, and all this is spraying out, okay? And we actually had the Cassini rocket travel through the spray of this Enceladus. And you can see, so NASA is calling it a ice or water world because they're saying that under this hard crust of ice that has a lot of little cracks and fissures, all these lines here where it's broken up, and look at that chain of craters right there in the upper left, right? You can draw a line through all those, right? Must be kind of along a fault line and spraying out or exploding out. So it has a bizarre terrain, as that says. All right, let's go on. Castillo, the second largest satellite of Jupiter. So now this is one of the moons of Jupiter. We have a large crater with a smaller crater that's more well-defined. Happened later, right? Because it blew through the side of the bigger one. And yet there's also, this section is an uplifted dome in the center of the big crater. So that's an unusual feature that we wouldn't expect with a meteorite. But it can be explained if this is happening from within, right? It can bulge up. And you notice a lot of crater chains as well over to the right. Okay, so trying to end the crater debate, we've got 26 reasons here. starting on the upper left there, the V impact signature and ejecta evidence, the evidence of glass, right? We don't see glass lining hardly any craters. But there is glass where we've done nuclear explosions or large tonnage explosions, testing bombs for war. We do find glass under those types of large explosions. But we're not seeing it in like Arizona Meteor Crater. Let me jump over to the right. The tektite and living desert glass evidence, that was one of those explosions that we set off. And we did find a lot of glass in there. There's the crater depth evidence, the crater doublet evidence. I like those because that's the two craters near each other. I won't try to read through all those now, but there's a lot of reasons. So at the bottom there are impact craters and meteorite impacts do occur, but scientists cannot naively continue to assume that almost all are impact origin. Eventually, time and truth will win the day. And so as this kind of evidence mounts up, we can say that. Okay, so going into the meteorite model, okay, and this is a picture of what they claim is a meteorite. The UN meteorite model will answer the three following fundamental questions. Do meteorites fall from space as frequently as modern science presently believes? Do all the rocks presently called meteorites come from space? And what is the true origin of meteorite-like rocks? So we're going to try to answer that. So meteorites are identified in three different categories. They're stone, iron, and then stony iron. Okay, so three types. Now, do all rocks presently called meteorites come from space? So this is Comet Temple 1. The answer is no, but we'll see that. Usually, when we think of rocks in space, right, we think of these very rough, jagged rocks that have sharp edges, like asteroids. That's how we usually picture asteroids. But as we see, not only asteroids, but comets, they actually do have smooth edges. And you can see there's a lot of pock marks and like craters in that as well. But they were smoother. What is the origin of meteoritic-like rocks? Good question, right? How many minerals are in meteorites? Right? Because they're saying that they're made up of this iron nickel that you can't find on Earth. Many meteorites contain carbon. How much carbon is found on the moon? we don't find carbon on the moon. Okay? But if meteorites contain a lot of carbon, then it's possible that maybe they came from Earth. A cosmic origin would suggest a variety of compositions. However, we find just the opposite in meteorites, a very select group of mineral compounds. Okay, this is Wilhelmian meteorite, a great big one that they found. So why do the world's largest meteorites have no crater? Because they found this out in the forest, and there's no crater with it. But they say it's meteorite. So that's a good question. To answer this question and to find the real origin of meteorites, we have to answer two more questions. Where were meteorites made? And how were meteorites made? Okay? So because of the dog magma, that's the idea that magma is in the center of the Earth. It's kind of a dog magma, a dogmatic position of most modern scientists, that believe most meteorites show a history of melting. Okay? But what do meteorites look like when they melt? And this is an experiment that we did with some meteorites that melted. Now, I don't have any of those meteorites type rocks with me, but I will pass around this piece of sandstone where we did a similar experiment where we put a torch, you can see up in the upper left, that torch, to heat it up hot enough that it melts the rock. So you can feel on this piece of sandstone, you can feel it feels like sandpaper, and it's very rough, but then this black area, it feels more like smooth glass. So go ahead and pass that around so everyone gets a chance to see that. But on meteorites, right, they have some of that iron and nickel metal in them, so you can see it's beating up, it's melting. When we put a torch to those meteorites, it is melting the meteorites, but then it kind of cools in little balls or globs, right? Like droplets of molten metal, okay? And so that's what we're seeing here, what a real melted meteorite looks like after it's cooled, okay? And this is what it looked like before we melted it. And this is an interesting thing. You'll see this when they cut a meteorite open. A lot of times it will have this Widman-Staton pattern. Very interesting. And what I want you to think of when you see that, though, is that this is kind of like a metal crystal. If you think of it as a crystal, you can see those different crystals all kind of intertwine, growing in long, thin shafts like quartz crystals would, and in this case kind of interlacing in between. And the reason that I can say that you can think of it that way is because if this was a real meteorite and it's coming in from outer space, it's going to heat up because gravity's pulling it down so fast, like the space shuttle, and it's like getting hotter and hotter as it goes, so much that the outside would melt and the inside would get pretty darn hot, right? Metal conducts the heat, so that heat's going to go into the center. And if these meteorites get over 800 degrees, this pattern goes away. It melts. So you wouldn't have this kind of pattern if it ever got over 800 degrees. And any meteorite coming in from outer space would get over 800 degrees. And so all of these, so even though modern science claims this Widman-Staton pattern is a identifying feature of meteorites, it actually gives us a clue as to how this was formed as a crystal forming in water, and that if it gets over a certain temperature, that it would melt and therefore couldn't come in from outer space. Any questions about that? Okay. So no naturally occurring terrestrial rock contains iron metal or iron nickel metals. Therefore, if we find a rock that contains iron nickel metal, it is probably a meteorite. Okay. So that's what they said at Washington University. But the problem is then we find an iron nickel metal, this one from Zhangtunken, Russia. Okay? So this is a natural iron nickel metal. So we can't say that it doesn't form on Earth because we found it. Although meteoriticists would like to believe that nickel iron metal is not found on Earth, worldwide deposits of elemental iron nickel have been known since at least the 1800s. These include a place in Greenland, the United States, Russia, Germany, and New Zealand. Okay, and these regmaglyphs is where there's a fusion crust between the stony rock and the iron-rich metallic part of the meteorite. Okay, and the question is, how do those get fused together? This is showing, I think this is interesting because there's so many deep holes in this rock, right? I mean, it looks more like a lava rock, doesn't it? And yet, because of its metallic composition, they're saying it's a meteorite that came in from outer space. Yet, real broken meteorites like these do not exist, exhibit regmaglyphs, that fused part, right? So it's not fused with this stone. The specimens of the Sikhote-Alin meteorite shower are distinguished by their sharply marked, well-developed regmaglyph relief. A study of this relief established the important fact that the size of the regmaglyphs is closely connected to the size of the meteorite. Okay. So again, this is getting deeper, but as we study deeper, learn more, then we realize there's a lot of contradictions between what modern science is saying about how common and these meteorites are and their composition as we get in and study them more. So what we're saying is the origin of meteorites is actually ejectite formation down deep in these diatremes. We have hyperthermal conditions where the ejectite is created in this hypertherm, and it has the heated fault lines, and then it gets ejected as we get to that water source. The water turns to steam and ejects out. So there's concave minerals where we have these holes and depressions in them are common, and the hydrofountain origin of meteorites can also be seen here. We have glena, the lead, and then the mascarite, iron sulfur, and the schalurite is the zinc. Okay, so we got different types of metals, but you can see forming in little balls and stuff like that, very indicative of a water origin. We have metal surface formations made in a hypertherm, okay, and then being ejected out in the hydrofountain. Okay, does that make sense? Okay. Go ahead and speak up if you have questions you want to ask. Okay, why is the amount of water in this meteorite been almost totally ignored by researchers? Okay, another great question. Inclusion of aqueous fluids have been found in a series of meteorites. This discovery was completely unexpected and still remains thoroughly enigmatic or mysterious to modern science after several years of study. Okay. So, science has looked to the skies to find the origin of rocks and minerals, but the answer lies in the bottom of the sea. Right? There's salt. So, a fundamental question is an FQ. Who thinks that the Arizona meteorite crater was made from an impact? Should we raise the hands? Right? Well, the name of the crater is Arizona Meteorite Crater, right? So everyone thinks that it's from a meteorite, except a few UMers, as the answer there says. We do not think it came from a meteorite impact. And so this is the evidence against the Arizona crater impact theory. There's a lack of impact glass, a lack of melted evident meteorites. They mostly find these little tiny balls of iron, nickel, out on the edge of the crater. And there's a lack of residual vaporized material, because they say that this huge meteorite vaporized, turned into gas when it impacted. The presence of the Widman-Staton pattern in the meteorite pieces that they claim come from Arizona meteor crater, which we already said would melt if it really got that hot. The lack of shrapnel fragments, the lack of crater-embedded non-vaporized meteorites, because we don't find any meteorites in the bottom of the crater. They're all out on the edges. Multiple iron sources require multiple impactors and multiple craters. So we have different composition of iron in the meteorites. So if it was a big rock in space that came down, right, then it would all have the same iron composition. But because if it's coming out of the ground, then it could have lots of different compositions, because it could come from different levels, different sections with different amounts of water and stuff around it. So that's a good one, number 7. Number 8, the oblique true meteorite field. It's in a big oblique oval rather than in that pattern, that V kind of pattern. The limestone in the crater unheated by high-speed impactor, because there's limestone concentration down right in the center, as well as up on the edge. The absence of shatter cones and the amount of iron at the crater is insufficient to produce the crater itself. And of course they say it vaporized, but that's a lot. How does nearly 300,000 tons of iron-nickel meteorite vaporize without melting a tremendous amount of the contact rock? Right? I love this question because it just makes so much sense, right? You have this huge rock coming in from outer space at high speed, so high speed that when it hits, it turns to gas, right? So it vaporized. So it had to go from solid rock to a liquid to a gas very rapidly for us to not find huge chunks of it everywhere. And yet, as it's going through that process, the sandstone around it is not melting itself, right? And the experiments that we've done and from rockets where we can see impacts from NASA, we're seeing glass-lined craters, but no glass in this particular crater. And it just doesn't make sense. So these are the sizes of the rocks, right? This is Arizona crater volcanic spheroids, right? Little tiny pebbles of this iron-nickel meteorite. Arizona crater volcanic ash. And this is comparing it to Mount St. Helens. On the right-hand side there, we have from Mount St. Helens the ash that is found at 5 miles, 22 miles, and 250 miles away from the crater. But in the Arizona crater, it's very different, all right? The distance to the crater, we're showing it here at 5 miles and 3 miles, so not very fine by comparison to Mount St. Helens, which would be a small explosion by comparison, right? Okay, A slow-speed impact would have to produce many broken fragments and shrapnel like these specimens. Okay. Again, these are the rough-shaped ones, right? Maybe that's why we think asteroids are rough-shaped, right? And this is showing the crater. That little circle in the center is the crater. And notice there's no dots in that because they didn't find meteorites in that. And this is a graph plotting out where the meteorites were found. And you can see a big concentration on one side of the crater. So,
what's the significance of it all being on one side?
Well, to me, it makes a lot of sense if it's an explosion. Maybe the way the wind was blowing when it exploded. But let's see. There's probably a better answer than that, but that's what I'm coming up with. Okay.
Good off the top of your head.
Okay, thank you. All right, we'll go. We're going.
The angle
Of the ejection, yeah. It could come from an angle, right? But I mean, it is.
Or it depends on how big. I mean, the meteor crater is huge.
Oh.
Just the natural rotation of the Earth as it comes up and then it falls back down.
Oh, yeah, very true. Yeah, that's a good idea as well.
I'm thinking of you shoot a bullet in the air.
Yep.
And then it's got to fall. How much time is it going to take to fall back down?
Very true. Yeah, that's a good idea. We should try to figure that out. Yeah.
Can I get my name on the book?
Good. There you go. You should. All right. Earth rotation factor. Somebody's research study.
Or, how you're talking about the V shape.
Right.
Maybe that's one of the sides that the V comes out.
But
Well, the V is for impact.
the V is for impact. Right. And it would have a shadow region where we didn't have any meteorites, but you can see there are some meteorites all the way around, right? So, we should be able to draw a V where there's no meteorites behind it where it was coming in, and then and most of it is in spider-like extensions out the other side. But this is more clumpy. Even though it's more on one side, it's more of a clump, not a scattered line.
The same kind of splatter pattern, like if we used to take our garden hose and squirt the water straight up in the air.
Right.
You'd stand on the
Yeah.
way or whatever, and you'd get
It'd be scattered.
the
Yeah.
water splattering.
Yeah. So shooting up makes a lot of sense. Yeah.
Does meteor crater have that secondary ejection hole?
I'm not sure about that, but yeah, I don't know of one for sure. But yeah, that could affect one side more than the other. Okay, let's go on. Multiple iron furnaces require multiple impacts and multiple craters. Are there multiple craters at the Arizona crater site? Oh, there's the answer to your question. The answer is no, not multiple craters. So that one happened one time. Okay, and this is that strewn field we were saying is in kind of a big oval. So an elliptical distribution of impact debris left behind when large meteorites land on Earth. Every large size observed meteorite fall has left behind similar distributions of material. And it's following the laws of physics because it's coming in at an angle. So we didn't see that on the one from Arizona Meteor Crater, but this is one from a meteorite. And the arrow right through the center of that, pointing up to the top, is showing the direction that the meteorite was coming in. Okay. And it looks like the heavier ones are being exploded, going the furthest. So that's interesting. They've got smaller, lighter ones down here, and the heavier ones getting thrown further. Okay. Curiously, no well-formed shatter cones have ever been found in Meteor Crater. So here's the Arizona hydrocrater evidence. So we said why we don't think Arizona meteor crater is from a meteorite impact. This is why we think it is from a hydrocrater impact. One, the water source evidence, the bisecting fault evidence, because there's two crisscrossing faults. And is it likely that a meteorite would happen to hit dead center on those two crisscrossing faults? Not likely. But that is, right, we set a fault line with those pockmark holes and craters is very likely for craters that are formed from within the Earth. And so if we have a fault line going that way and the other way, crisscross form, then that's the weakest point. And so that's where it's going to explode. So bisecting fault evidence. A diatreme is the smoking gun because they actually did seismic studies to see where the rock is broken below the surface of Arizona meteor crater, and they found that it was in that diatreme funnel shape. And there's a picture of it in the Universal Model book. The volcanic district evidence. We know of a lot of craters that are formed from volcanic activity and faults and explosions. There's probably more than 90 craters within the four corner states. And so all of the others the world recognizes as explosion craters, and this one is the one they say, nope, that one came from a meteorite. The shell ball evidence, they are not meteorites, big balls of shell. Diamonds are known to form only in diatremes, down deeper in the diatremes. And pure silica, the second smoking gun, the pure silica they find right near the bottom center of the crater, and then some on a ridge on the outside. So, and it's very pure silica. That would be like sand, or like pure quartz crystal type sand. And we didn't mention it here, but actually the vegetation grows in a circular pattern down near that center. And I believe that's because you still have steam escaping through that diatreme and watering the plants in that bottom circle area. So since I was up there, I noticed that. Even in the drought that we have now, you can kind of still see where there's more vegetation in a circle around that area. Okay, so Barringer discovered this as he tried to penetrate below the surface of the crater over a century ago. In passing, I should say that it was found impossible to sink our main shaft more than 22 feet, or about 25 feet below water level, because of the particular quicksand formed by the water-saturated silica, which we encountered. Also, that, in my judgment, it will be impossible to properly explore the depths of the central portion of the crater until we have removed the water, which we now know fills its lower portion. So, I think the way that they were digging this tunnel is by lowering a person down in there and digging it out, right? So it's a lot of manual labor. And so it's a fairly big hole that they've dug. And so as they got too deep, it's like a well. It fills up with water. As it's coming, the water comes through the silica dirt around the side. So that's what he said about it. This is showing you those diagonal fault lines in the crater, and it creates it so it's kind of a square shape too. So the fault lines crisscross across like that, and you can see them from the edge. So again, it hit right in the center, and it's unlikely that it hit in the center. More likely that it blew it out in the center, and it makes sense then that it's more squarish than roundish shape because it is blowing the weak points out. What definitive proof can distinguish an impact crater from a steam eruption crater? And the answer is the diatreme. And who remembers what the diatreme is?
The lava mixing with the water, and then it turns steam and it's floating out.
And it forms what shape? A funnel. Yeah, a diatreme, but the funnel shape. Okay, is what you want to think about. Okay, so this is what Shoemaker said. It's his diagram, and it's showing how they're drilling these holes down in here because they figure the rock was cracked and broken in a bowl shape beneath the crater. So this is the edge of the crater, and this is where he thought the ground was broken down to. And so he's thinking if he could drill down through that, he was hoping to find a huge meteorite, iron nickel meteorite. He'd figure he'd make a lot of money, right, in the Iron Age when trains were going by there. So they dug down and said they went down 700 feet. I think that's questionable, but anyway. This is showing modeling of a bowl-shaped fracture zone from actual impacts, like from bullets, right, being shot into the ground surface. And you can see imaging that in a couple different ways. Those impacts do form bowls, just like Shoemaker expected in that last diagram. The question is that what we're actually going to find? And so these three researchers did their research, and they claimed that the fracture zone was this bowl shape that was inferred from Shoemaker's drawing. But then drilling by Behringer and his associates did not pass completely through that fracture zone. So going back to this picture, they didn't dig deep enough to get through that fracture zone down to bedrock. So we don't really know if it's a bowl shape there. And Shoemaker claims ordinary siltstone and sandstone were obtained at depths of 750 feet deeper. So he's claiming he got down past that 750 feet, and he's claiming that it was ordinary sandstone or siltstone down there. So it was like the original rock undisturbed, is what he's claiming. But the actual seismic study proved that rocks are fractured to a depth of at least 800 meters, much more than the 700 they dug to. So 2,625 feet beneath the crater floor. So, and that's coming from the seismic studies. And so here is the picture of the study that these researchers, Ackerman, Goodson, and Watkins did. And what would you call that shape? A diatreme. Yeah. All right, everyone together. Diatreme. There we go. So you can see it's a funnel-shaped cone. So it's broken way out to the sides here at the top, because as you know, first you start with a steam explosion, but then it's starting to push rock, right? And so these rocks now are pushing against the rocks above them, and that's why it breaks out way out to the sides here, because we're breaking through that stony surface of the ground. And but way down past 800 feet, that's as far as they measured, but we don't know how deep that goes. We didn't measure it further. And so that's another thing we need to do, because I think it goes much further than that. But that's kind of that smoke and gun, right? The funnel-shaped evidence. Okay, so this is Shoemaker talking about his impact, and the scientific knowledge is not absolute. So he can point to it and he can say that it's a meteorite impact, but can't be proven. Okay, and we're really, I think, running out of time here, so I probably need to skip through a lot of this. This is finding diamond with the meteorites, and diamonds form deeper down in those diatremes. Here's the evidences stacked up, 11 different factors saying against the Arizona meteor crater coming from a meteorite. And again, here's our list of hydrocrater evidence that we talked about. So in the testing of hypothesis lies the prime difference between investigator and a theorist, right? Shoemaker was really a theorist because he didn't do the research and find that. Okay. So I'm going to just kind of skim through some of the rest of this. Basically what it goes to, what celestial body contains craters like this? Do you recognize that? Yeah, it's pancakes. All right. I actually called them hydrocrater capes and made them this last Tuesday. I made them with my class here at American Family Education. We looked at those, and one of my students was saying, yeah, they came from a meteorite. And I was kind of asking him, well, now how did that come through the roof, though? And so I had him watch a little closer the next batch that I cooked up. But anyway, impact to hydrocrater evidence. Obviously, those craters and pancakes form from steam. Okay. Again, I don't have time to really talk through these. That's showing you some of the ring craters that we find, and also the magnetic intensity through radiomagnetic imagery is showing that it's coming through that center shaft of the crater. Oil wells happen to be just outside the crater rim, and they are often found together. Again, I can't read through these. This is another hydrofountain where you have this column that's hollowed out, and yet it's turned to stone around it as kind of like a sluggish pipe. If you think of it that way, it started to slow down the flow from that crater, or that hydrofountain slowed down and started to turn to stone. A dome crater. Again, this is the big central uplift. Makes a lot more sense if it's coming from the center. Again, this is looking at some of the places in our solar system. Hydromoon. And NASA actually had news on primetime television talking about them confirming that there is ice under the surface of the poles on the moon. So they're actually confirming what we're saying here. But I don't really have time to talk much about it. Okay, real melted basalt looks like glass, and yet we find these basalts. This is the near and the far side of the moon, and as we look up at the near side, it looks like oceans. That's why they're called Mars. M-A-R-E there, because they were thought to be oceans. And they're on our side of the moon because gravity would tend to pull the liquid towards this side of the moon. But it's so small that liquid evaporates off, and so that's why the surface of the moon is very dry. But looking at this, I mean, you can see that that's like dried and cracked in this crater. And you see a lot of the features that we talked about. Here's one of those target-style craters. Some that have out channels, like the Mount St. Helens, dug a canyon out the side as some of that mud or fluid flowed out of the crater. The gravity evidence, notice how different those Mars look, right? So that's based on gravity measurements. Okay, comets also. How are comets formed? And we went and experienced Halley's Comet close up. We have, you can see on the bottom left there, there's one with steam explosions coming out. Okay, so the tail of the comet is from the water or steam that's being ejected from the crater. So we're confirming as we study more, right? In fact, you can see how rough that one is because that's somebody's drawing of a meteorite or a comet, and this is an actual comet, much more smooth edges. But we found that 72 trillion kilogram nucleus was extremely porous, with as much as 80% water, or volume taken up by empty space, but it would have had water in before it was blown out as the comet fizzles out, I guess. All right, but that's what we think asteroids would look like, but this is what real asteroids look like. Okay, again, smoother and pits, probably exploding of the center. Here's one with a big crater that's almost as big as the asteroid itself. Okay, so where are the impact craters? This one, the bumps are the opposite direction, right? They're going out the other way. Okay. The conventional definition of comets and asteroids are in need of refinement, need to be changed and fixed. Okay, again, I don't have time to go through all of this, so I'm going to zip through. Oceans is another frontier. We can find a lot more about our world looking at that. So again, we need to study the depths of the ocean because we are finding, like the deep thermal vents in the bottom of the ocean, we're finding that some of the rocks are being formed around those because they're in that deep ocean and with hot water. So you got pressure, water, and heat. From seismic observations, geologists know that the Earth's crust or lithosphere is floating on a liquid. So without magma, what other liquid could the crust be floating on? One of you want to answer that? All right, water. You guys got it. So, and how much water is in outer space? We actually kind of talked about this last month. We were talking about all the water in space. So again, I'm going to kind of skip through. I think that gets us to the end. All right, so thank you very much. Do you have any questions for me?
So at some point, the moon had to have ejected a lot of water?
Well, so the Earth is big enough that when water evaporates off the surface, it gets trapped in the clouds. And the gravity keeps those clouds close enough to the Earth that they can later rain and drop the water back onto the Earth. But on the Moon and on Mars, there's no atmosphere because they're smaller than the Earth, quite a bit smaller. And so the gravity is left so the astronauts can bounce across the surface of the Moon, but when the water bounces off, it just keeps going. It's not heavy enough of a molecule for the gravity to pull it back down. The astronauts, fortunately, are heavy enough that they get pulled back down, but the water just goes off. And so that's why the surface of the moon is kind of powdery and dry, because it's dehydrated so much. So they still are finding ice under the polar caps, and there's probably a central core of water like our picture showed. But at one time, there would have been some oceans on the surface of the moon. And as you look at the craters, a lot of them look like the mud pots that you see in Yellowstone. So.
I kind of wondered if maybe at the same time we had the flood, maybe the moon was doing the same thing.
I think there's a great possibility of that. Yeah. Yeah. Mm-hmm. Yeah. And that may have been a time where some of the water was taken. You know, the Earth grabbed some of the water from the moon and dried it up more. So, yeah. And as you look at the craters, a lot of them look like, you know, maybe they were formed underwater. You know, they look a lot more like the craters that are found in the bottom of the ocean than one that's formed in dry dirt. So, great question. Any other questions? Okay. When's the test? All right. You're actually welcome to join my Science Study course. I'm actually teaching an online class now, so anyone in the world can take it, and you can just sign up. I'm just kind of coaching people along. You get the book, read through what you want to. We also have the summary book, which covers all 3 volumes of the Universal Model, and those are only $5. And the Universal Model, Volume 1 here is the Earth system, and we covered 1 chapter today, Chapter 7. Next month, on the 4th Thursday of the month, we will be back here covering the Universal Flood chapter, Chapter 8. And then in October, we will do the weather model. So we'll be introducing new ideas about weather that are really exciting. But there is another, Volume 2 is the living system, and Volume 3 is the universe system. And those are all kind of summarized in this little book, too. So any of the books that you want to read, I'd be happy to coach you along and help answer your questions. The idea is you tell me what pages you read and what you thought of it, or questions that you have, and I'll read through that and give you some comments and ideas and suggestions. And I'm trying to get like a online phone call, video conference together with all of my students in that once a week on Thursday mornings at 6:30. But let's see, and I also am teaching the experimental class for the young students here, but other people are welcome to come. That's Tuesdays at 1 o'clock here at American Family Education. And I certainly appreciate American Family Education for allowing me to use their building here and their facilities. And thanks to Darren for doing our video today. And that will be posted on our YouTube channel, Do True Science. So you can check it out there or refer other people to it. Did you have a question? No? Okay.
For the beginning of this, it's important to know this thing, so I'm exposing my ignorance for you.
Okay.
And that is, what makes the so-called universal model universal? What is the definition of it?
So, because it's looking at all branches of science, the author considers himself an omnologist, studying all branches of science, and he's actually making new discoveries in, this chapter is all about geology, And he's claiming Arizona meteor crater is not from a meteorite impact. That's pretty dramatic, revolutionary, and hopefully I convinced you that that's true. And he's finding things like that in chemistry and physics and biology and the weather. He's come up with a new source of weather that meteorologists have completely missed. So it's pretty phenomenal. In fact, he's reversed the philosophy of weather and has the high pressure systems coming down and piling up and pushing down, causing high pressure zones. But you'll find that we say that it's high pressure is coming up and out. So completely opposite thinking, right? Ice water core in the center of the earth versus molten magma in the center of the earth. Completely opposite. And yet, he's coming up with all of the research that has been done by other scientists and all the quotes that we're finding to back it up. And so he's claiming to come up with dozens of new scientific laws, and also shows in the book that we haven't had any new scientific laws for the past 150 years in science, because the scientists have just accepted the theories of modern science, that there was a big bang explosion that formed everything, and then all these chemicals got together and formed life, and life evolved from all the single-celled organisms into all the plants and animals, and then into us. So he's saying that's wrong, and he's showing us why, and how we know that's not accurate. Yeah. All sciences, I think. Yeah, no, yeah, it's not. Yeah, it's for the whole universe, right? And as a consistent, there's one of the slides that is a puzzles pieces. He has puzzle pieces all put together, and he says that nature looks beautiful and makes sense and all fits together, but modern science's picture, he has puzzle pieces that have a lot of pieces missing and out of place, and it doesn't fit together and doesn't look like anything you can really recognize. So he's saying it's cohesive and fits together better than what modern science says as well. Yeah, great question. Okay, yeah.
Did you tell him how long it's been in the hospital?
27 years. Yeah.
And why you wrote it?
He was told in 1990 that he would never find any scientific evidence of the universal flood. And he's thinking, well, man, if water covered the entire surface of the earth for a year, it'd kill off a lot of animals and plants, and there'd have to be evidence, right? So, but his professor told him that he wouldn't find any evidence. And so he thought, that can't be right. And so now there's more than 223 pages of scientific evidence of the flood. And we'll be covering that next month, so come back. Thank you very much. Yeah, I'm excited about it too. Thank you.